Hi, today we are going to solve one more question about chemical equilibrium constant. Okay, as you know that on the right hand side in the blue box there are answers. Okay, the marking memorandum answers here. But what I want to do is that I just want to answer question 9.1 and then 9.2, and then you can see how we can answer 9.2. Okay, anyway, so let's start with question 9.1. The thermal decomposition, which means that it is going to break down into components. So there's one big substance, it will become two or more substances into smaller structures. Thermal means by using the heat energy, okay? And calcium carbonate, and the calcium carbonate will turn into calcium oxide and carbon dioxide gas. And then is an example of heterogeneous equilibrium, okay? Heterogeneous equilibrium means that we don't have only one state of or phase of substance, okay? If you remember the previous questions, we were having only gas, only aqua in the question, okay? Only solutions, only gases in the container, okay? And the most of the questions are only gases, okay? Reactants are gas, products are gas. So only one phase is what we call as homogeneous equilibrium, okay? If there is more than one phase, as you can see here, okay, there is solid here and there is solid and gas. So more than two phases, more than one phase, it becomes heterogeneous, okay? And the decomposition takes place in a closed container. Yes, that's one of the conditions that we must have for chemical equilibrium, represented by the following equation. And then as you can see that it's a balanced equation, you can check that. And the coefficients are 1, 1, 1. So the mole ratio is 1, 1, 1. And initially 15 grams of calcium carbonate, okay, the reactant you add 15 grams is placed in a 4 decimeter cube container. Container volume is 4 decimeter cube and then heated. And then it decomposes, producing this, and at the same time, these two producing that, okay, after a while. That is how we have rate of forward reaction is equal to rate of reverse reaction when the equilibrium is reached at 800 degrees Celsius. And then I'm going to calculate the mass of unreacted calcium carbonate that remains in the container if Kc for the reaction is 0.03. So they gave us Kc, they gave us the initial amount of reactant on the left-hand side, and then volume of the container. They want us to find out how many grams of calcium carbonate will be left after the equilibrium is reached. So when I go onto my slides, if I go onto my slides, when I look at the table, okay, when I look at this table, that's what we call, if you remember, the Rice table, okay, this is Rice table. I'm just going to highlight now. Up to down, Rice table, okay, there is R, I, C, E, E, and double E, Rice with double E. And then initially I'm using my, okay, I'm just going to change something, okay. Initially I'm using my, okay, I'm using my mole ratio. By using the coefficient, I'm going to calculate the mole ratio, 1 mole, 1 mole, and 2 moles, okay. Actually 1, 1, 1. I don't know why did I write 2. I'm not sure. Okay, it's supposed to be 1 mole, by the way. Sorry, I made a mistake here. Can we fix that mistake? Okay, let's fix that mistake. It's supposed to be 1, by the way. Okay, let's go back to the presentation. And then, so what do we see here is that initially we have 15 grams and Kc is 0.03, volume is 4 decimeter cube. And then I'm looking for how many grams will be left at equilibrium, okay? If I can find the number of moles of CaCO3 at equilibrium, I'm sure I can find the mass of CaCO3, calcium carbonate, okay? That's what we are going to do. First of all, what is given is that, okay, 15 grams. So this one tells me that I need to convert it into number of moles. If you look at the right hand side, okay, if you look at the right hand side here, okay, so in this calculation, so N is equal to M over capital M, molar mass, sample mass over molar mass. Sample mass is equal to 15 grams and the molar mass is 100. Calcium carbonate, if you calculate it's 100 grams and 15 divided by 100, you can easily calculate 0.15 moles. So we convert it into initial amount into number of moles. And then imagine that until it reaches equilibrium, okay, until it reaches equilibrium from 0.15 into equilibrium, okay, and Y mole of, okay, calcium carbonate use, and then Y mole of carbon dioxide will be produced, okay, and what is the mole ratio between these two? 1:1. Okay, imagine that if we say we don't know how much use, that's why we call it as Y, okay, so and so which means that 0.15 moles minus Y moles, it's going to be the equilibrium number of moles is going to be 0.15 minus Y moles. And then if I can convert this number of moles, okay, if I can convert this number of moles into grams, that is the answer for the question, okay? So I use Y moles. And what is the mole ratio between calcium carbonate and the carbon dioxide? Okay, ratio between these two is 1 and 1. If I use Y moles, and then I'll produce Y moles from this. Can I also say that I will produce Y moles from the calcium oxide? Yes, I also produce Y moles of calcium oxide. Okay, I can produce the same amount. I didn't write here because there is no need. I'm going to show you how. Okay. So if I produce Y moles, initially how much do we have? 0. Okay, we said that if it is not mentioned in the question, from products we always have 0 moles. Okay, initially we have 0, you produce Y moles. How many moles we will have at equilibrium? Y moles. And then if I convert these Y moles into concentration, how can I convert into concentration? Y moles, C is equal to N over V, Y divided by 4. It is because the volume of the container is equal to 4. Y divided by 4 is going to be the mole per decimeter cube is going to be the concentration of this CO3, carbon dioxide gas at equilibrium, okay? That's what we did. Why didn't I calculate this one and this one? Because their concentration is always equal to 1. Why? Because these are not solutions or gases. Okay, their concentration will not change, okay? So that's why there is no need to calculate this. There is no need to calculate that. Why? Why there is no need to calculate? Because in our, okay, in our KC formula, okay, in our KC formula, what we said, okay, in our KC formula, we don't use solids. That's why I highlighted here. We only include the solutions and the gases. As you see, there's only one gas, that's carbon dioxide. So that's why I didn't calculate others. I only calculated Y over 4 mole per decimeter cube. That's the concentration of carbon dioxide at equilibrium, okay? So what is the Kc formula for this? Kc is equal to the concentration of carbon dioxide, and then the coefficient in front of CO2 is 1. So that's why the power is 1, okay? And so what is the Kc and divided by reactants or products, okay? These two are solids, that's why you don't use these in the formula, okay? In the formula only gases and aqua, okay? So only solutions and gases, that's why others not included in the Kc formula. So which means that Y over 4 is this, the concentration of carbon dioxide at equilibrium, power is 1, is equal to 0.03 is given in the question, okay? And then if you do cross multiplication easily, there's always 1 here in the denominator, and then Y is equal to 4 times 0.03, that's going to be equal to Y is equal to 0.12 moles, 0.12 moles, okay? That is our how many moles of, okay, carbon dioxide at equilibrium, how many moles carbon dioxide produced until it reaches equilibrium, how many moles of calcium carbonate will be used, okay, until calcium carbonate reaction decomposition of calcium carbonate reaction will reach equilibrium. Okay, so we want to calculate this. Okay, I want to calculate this. Can I just clean up here? Okay, let's clean up here. So we want to calculate this. To be able to calculate this, I need to find out 0.15 minus y. I already found y if you look at right hand side. So 0.15 y minus y moles is equal to how many grams? Oh, that's my question. Okay, and how much left after it reaches equilibrium? Okay, 0.15 minus 0.12, we just calculated that. Okay, that we write down here. So which means that 0.03 moles of CaCO3 is how much? Okay, so that's the question that we need to ask. Number of moles is equal to sample mass divided by molar mass, and 0.03 is the mole number is equal to the sample mass. That's what we are looking for, divided by 100. And if you have one denominator here and then cross multiplication will give you 0.03 times 100 is equal to m times 1. So m is equal to, this is not capital M by the way, okay? Because of typing, okay, it happens. Okay, sometimes you type and then it makes it capital. Okay, let's fix this. So this is the sample mass, sorry. Again, same. So this is the sample mass. That is how we okay, answer the question. So the X, okay, amount left is how much? 3 grams. Okay, if this one is 3 grams, can I just go back and then check? Okay, if this one is X is 3 grams, and then how much will be used? Can I also calculate that? Yes, how much in grams? Initially, how many grams we have? 15. And finally, how much left? 3 grams. So which means that 0.03 moles of is used, sorry, 0.12 moles used is equal to 12 grams, okay? So 12 grams used to be able to reach the equilibrium, okay? That's how we can calculate. And I just want to do the second part of the question before we finish, okay? I hope that this one is going to help you. Okay, this is our last question for this topic. So it is found that the value of Kc increases when the container is heated. Okay, when the container is heated, okay, what happens is that, that's what we are going to discuss. Look at the answers, okay? Okay. When the container is heated, which means that you increase the temperature. Is that correct? Okay. So you increase the temperature, a higher temperature. So when you increase the temperature, what will happen? According to LCP, Le Chatelier's principle, an increase in temperature will favor the endothermic reaction. So according to the temperature, okay, increase in temperature, according to LCP. So you increase the temperature and the reaction will decrease the temperature by favoring, okay, by speeding up the endothermic reaction. And then is the forward reaction or exothermic or endothermic? Use Le Chatelier's principle to explain your answer. It's found that the value of Kc increases. So Kc increases. So we just said that. Okay, we just said that according to LCP, and then increase in temperature, and the reaction will do the opposite one, decrease temperature by favoring endothermic reaction, because endothermic reaction absorbs the reaction. And then what happens to Kc? Kc increases. How will Kc increases? Look at here on the top. Kc depends on what? Concentration of carbon dioxide. So if you look at the reaction here, if the concentration of carbon dioxide increases, in which case concentration of carbon dioxide will increase? Only the forward reaction is favored, will increases, produces more carbon dioxide and increase the concentration of carbon dioxide. So which means that increasing Kc means that forward reaction is favored. And in the increase in temperature will favor the endothermic reaction, means that the forward reaction is endothermic, okay? The forward reaction is endothermic. So when the temperature was increased, Kc increased, therefore the concentration of carbon dioxide increased and more products are formed, therefore the forward reaction was favored. So which means that forward reaction is endothermic reaction, okay? The forward reaction is endothermic reaction. So what is our answer for 9.2? Endothermic reaction. Okay, this is another type of question that we can have in KC calculations. Okay, thank you very much. Okay, I'll finish up here.